Okay, good morning, everyone, and welcome to our final lecture session on linear models. This is a big topic to try to fit into one class, so it's going to be a fairly conceptual and rapid overview of a big topic, and hopefully enough to give you some framework to go in deeper and tackle the linear models that you need to use for your research. So we'll spend most of the time on chapter 5, the linear models section, just picking and choosing from there. And we will just very briefly, in a few minutes, touch on high-dimensional data. This is an example that the textbook uses on the application of linear models, which is a nice one because it is it's a fairly intuitive example, and it's a kind of a cool one. The reason I don't go straight into high-dimensional data sets and such is because it becomes harder to visualize what we're talking about, even though the models are the same. So this model is a perfect analysis of variance type of model, where the authors Wolf and Gorb in this paper, they took very detailed electron microscope pictures of the legs of a spider, and they observed a bunch of different spiders walking and measured the actual coefficient of friction of each of the legs as they pushed and pulled. So these spiders have 8 legs, and the forces, the friction forces, were measured in pairs. So this is a figure taken actually from their paper. Thank you. A very cool picture taken from their paper, where they have 4 columns for each pair of legs. This first column corresponds to the front 2 legs, and the first row here is a bar chart showing the total area of these feet. So you can see that the area of the feet increases gradually, and then a fair bit for the hind 2 legs. So those hind feet are bigger than the other ones. And these are their actual measurements of the friction coefficient. So you see, and they've measured it both for when the leg is pulling, so if they're climbing on something and having to use the legs to pull, versus when they're standing level and are using it for pushing. So these are very versatile legs. I wish I had feet that could do that. So this is why they got into science. I mean, they actually measured these infinitesimal forces pushing and pulling by each of the legs. And so this box plot is showing over a number of replicates of spiders. These are the pulling coefficients of friction and the pushing coefficients of friction. So for these front 2 legs, you see that there's variability, but generally pulling is going to be more effective than pushing, or there's a greater coefficient of friction when they're pulling. And then as you go back to the second pair of legs, that pattern is more or less the same. They're both a little higher here. The third leg, the pulling friction is higher yet, but the pushing is back down to where it was. And then for the hind legs, pulling is even higher yet. So there's a bit of a trend here for the pulling and not so much for the pushing. Things are a little bit here and there for pushing friction. Is anyone? Oh, whoops! What happened? It thinks we should get some sunlight.
Yeah, I'm not sure where they were there. Somewhere here.
I originally closed it from back there.
So why is it working?
I don't know. Sorry, everyone who's online, we're just having some technical difficulties here. Yeah. It just happened automatically.
Yeah, sometimes it's just, I don't know how other things there is some kind of user frequency. There's too much dark inside.
It's like, it's a nice day outside, we should open the shades.
It's okay.
Can you see it well enough?
Yeah.
Okay. So here are some of their research questions. Are the pulling and pushing friction coefficients different? It certainly looks like it in this box plot, but we'd like to have a statistical test for that. It's not always going to be so obvious. Are the friction coefficients different for the different leg pairs? Maybe. And it seems to depend on whether it's pushing or pulling, whether they differ. Or does the difference between pulling and pushing friction coefficients vary by leg pair? So this difference between pushing and pulling, is this, you know, more or less the same for each, or is that difference changing? These are all questions that we can address by linear models and by analysis of variance. Let's take a little look at the data set, my exploratory initial analyses that I like to do for a new data frame that I have, a table, so a two-way table of the leg variable and the type variable. So we see there are these four, L1, L2, L3, L4, for the four leg pairs, and pulling and pushing. And you can see that that it is balanced in that for each leg pair, there are equal numbers of pull and push measurements, but it's not balanced by the number of measurements on each leg pair. It was a little harder to get measurements for L2 and easier for L3, or for some reason there are different numbers of measurements for the different leg pairs. And taking a look at the summary, here are just the one-way frequency tables summarizing the overall numbers of each leg pair and the types of measurements. Then there's this third column, the friction coefficients that you see varying down from a minimum of 0.17 to a maximum of 1.84. So we have one categorical variable with 4 levels. We have one binary variable with just pull and push, and we have a continuous variable of friction. And this is a fairly classic setup for a linear model where we have a continuous variable as our response and some combination of continuous or categorical or binary variables as the predictors. But this is going to be the typical case, and all of the cases that we'll cover today will have a continuous variable that is the response or the thing that we measure. Let's make that box plot ourselves. It's not too hard to do with the box plot function. I just put this in here so you could have an example and be able to reproduce what they did in the paper. Using this tilde, this is what we call a model formula interface that I'll be telling you more about today. And you don't have to use it when you're plotting, but sometimes it is nice because it's it is consistent with the way we specify linear models when we're doing the statistics on them. It's specified in the same way. So just from our exploratory analysis, we've learned what variables we have, how many of what the possible values of each variable are, and the balance between pushing and pulling, and the number of pushing and pulling measurements that we have for each leg pair. And by looking at the box plot, we can immediately make some probable conclusions from the data set, including that the pulling friction is higher than the pushing friction, and that there seems to be a pattern when the legs are pulling, and that friction increases as you go towards the hind legs, but that pattern doesn't exist so much in the pushing friction. And this is another nice aspect of this data set, and that this is what we would call an interaction or an effect modification, in that the effect of the leg pair is modified by whether you're talking about pushing or pulling. There's an effect present for legs pulling that is not there for legs pushing. That is an interaction which you'll learn how to model today. And one other thing to notice, which isn't directly related to any of the research questions, but is that the variability of measurements is not constant. So there are some, especially among the pushing, there are some of them that have very little variability. Leg pair 1, 2, and 3, not very variable, and then leg pair 4, there's quite a bit of variability. Mm-hmm.
So do we have to test if they have a normal distribution?
Good question. Do you have to test that they have a normal distribution? I advise, and I think most statisticians advise, that you not do a formal test of normal distribution, even though one of the assumptions of the linear model is that the residuals are normally distributed. The general diagnostics and advice is to do plots. What's that? The diagnostic plots. I didn't put those in the slides, but we can take a look at the diagnostic plots. The reason that tests of normality are not very useful is this. The linear models and the inference that you'll do from them, especially the F-test, the t-test, these are fairly robust to departures from normality, especially when you have large sample size. These tests of normality, however, the larger your sample size becomes, the more sensitive they become to departures from normality. So if you have n equals 1,000, you can detect a very small departure from normality of your residuals, but it will make no difference for your inference. Whereas for a small sample size, if you have n equals 6, then your test for normality is not likely to detect anything, but that's where it actually matters. So you have this paradox that you can detect departures from normality when it doesn't matter. And so I don't recommend them, but what I do recommend is the diagnostic plots, and just qualitatively assessing how close to normal your residuals are. And that comes with it comes with experience. It's a good thing to, when you're doing it for the first time, to show to someone who has been looking at those diagnostic plots for longer, and to just build experience looking at them and getting an idea of what is okay and what is really too big of a departure from normality to accept. Very good question. Oh, and I just wanted to mention this note that the variance isn't constant. That violates one of the assumptions of the test that we'll be doing, which is so-called homoscedasticity. Homoscedasticity means that the variance in each of your groups is the same. So it is probably violated here, but it is also not a huge issue in that the tests that we will be doing are fairly robust to departures from homoscedasticity, and they're also conservative. The tests that we'll be learning have been a bread and butter of statistics for more than 50 years now, and these are part of the reasons that the tests are robust and conservative, very useful tests. So what are linear models? In a linear model, we have a response variable, which in this case is going to be the friction coefficient that we're going to model as some linear combination of the predictors, which in this case are the leg pair, 1, 2, 3, 4, and whether it is pushing or pulling, plus randomly distributed noise, which, as you pointed out, we usually will assume is normally distributed noise. So I've written 3 equations down here, and I want you guys to guess which of them are examples of linear models and which are not. The first, that's definitely a linear model. Yeah, the second one is as well. Very good. That was a bit of a trick there because there's the xi squared, but it's still a linear combination of each of these predictors if you think of x squared as another predictor. What about the third? Yeah, very good. No, this is definitely not a linear model because we have this exponential dependence on x. This assumption of normality is described compactly in this equation at the bottom, where the residuals are distributed. IID means identical. They are independent and identically distributed as a normal distribution with 0 mean and a constant standard deviation. So I'll cover what this means. This is a very compact representation of assumptions of the linear model, so I'll detail it later. So yes, the first 2 are your examples of linear models. This is a general representation of the multiple linear regression model, which can have any number of predictors. We'll write it as 2 parts, the systematic part of the model, and I'm using some notation really introduced in this class, but this E stands for the expected value of Y, your response, given any combination of your predictors X. So this is a systematic part, meaning that you're predicting the expected value, not the noise. And that is modeled here as an intercept plus a linear combination of your predictors from 1 to p. And these betas are the regression coefficients. So they will define what the linear combination of the predictors is that predicts your expected value of the response variable. I'll just let you look at this for a moment. It's a bunch of text, but this is if we divide this model into two parts, a systematic component and a random component, this is a complete representation of that systematic part of the model. And then the random part is just adding to that systematic part the residuals. And this reflects the fact that experiments and observations always have some unpredictable component, either due to measurement error, due to unmeasured predictors. We, in general, can't and don't want to predict exactly, because there is most likely some component of the model or of the data that are simply not predictable. So the assumptions of the linear model are very compactly represented with this little formula saying that the residuals are independent and identically distributed according to a normal distribution with zero mean and a constant standard deviation. So breaking that down, it's the assumption that the residuals are normally distributed. And remember that this is the residuals that are normally distributed. It's not necessarily the response variable itself. And this does matter sometimes. If you remember that, those box plots of the pushing and pulling, you might, where there's a big separation between them, you could imagine that maybe the residuals from in that model would be normally distributed, but your response variable would be bimodal, because you have low values where for the pushing, high values for the pulling. Your friction values themselves are not normally distributed, but if the residuals are, you still meet this assumption of the normal distribution. The mean of the residuals is zero at every value of the predictors. This is a statement that your assumption of linearity is correct, that there isn't bias, so that at some values, if you fit a linear model to some nonlinear relationships, then you will end up with it at overall your residuals will be centered on zero, but at some values of the predictors they will be positive, and at other values they will mostly be negative. You can imagine trying to fit a straight line to curved data, and your residuals will, your data points will be all above the line at some point and below the line at other points. So this second one is a statement of linearity of your data, and it's also contained in this compact representation. That there is constant variance at every value of the predictors. That's this sigma squared. So the residuals have just one value of the variance. That is the statement of homoscedasticity, to use a big word for it. And then values, residuals, they're statistically independent. That's this IID statement. And that's a very important assumption, that each of your observations are independent of the other ones. And if you violate this assumption, and there are many examples in the published literature where people have done this, it's often called pseudo-replication, where you have something where your data looks like or could be treated like independent observations, but they are not. This can give you very biased p-values. Just as an example of a way that might be violated, would be it actually would maybe somewhat violated in the models that we do today. I think not in a serious way, but in the measurements of legs from the same spider are not going to be independent. Really, that should be incorporated into the model, a grouping of the legs according to which spider they came from. If these measurements weren't each from a different spider, we may be violating, and we don't incorporate for that in our model. We may be violating that, but we don't have the tools yet to deal with it. That would be under the context of what we call random effects models, hierarchical models, and it's a bit more complicated to deal with. So these X, they can be any kinds of variables we want. In general, the Y for everything that we covered today is going to be continuous, but the X, they can be continuous. And for continuous variables, we can just leave them as is, or we might scale them to unit variance, which results in what we call adjusted regression coefficients. And for continuous predictors, we will get a coefficient, and the way we interpret that coefficient is it is the amount that the response variable changes for 1 unit of change in the predictor. So if the predictor were, say, if we had the weight of the spider in milligrams, then with as-is coding, the interpretation of that coefficient would be how much the coefficient of friction changes per 1 milligram change in the weight of the spider. And if it were scaled and there are adjusted regression coefficients, the interpretation would be the amount that the friction coefficient changes per 1 standard deviation change in the spider weight. With binary predictors, such as the push-pull in the spider legs example, these get coded as dummy variables with 0 and 1. You don't have to do this yourself. R does it for you if you have coded the variable as a factor, but it will happen behind the scenes, and you'll get to see a bit about how that happens later. The important thing, though, is that there is a reference category, the one that gets coded as 0, and then there is an alternative category, the one that gets coded as 1. So either push or pull will become the reference category, and the other one be the comparison category. So here that's written out. If we make pull the reference category, then all of the pull values get coded as 0, and the push values get coded as 1. Finally, we can have categorical predictors with more than 2 levels, either ordinal, meaning that they have a number. We could argue that the leg 1, 2, 3, 4 is an ordinal variable here, or a nominal categorical variable where there's no ordering. And the coding for this in general is that if we have a k-level categorical variable, it will get coded as k-1 dummy variables. So for our four leg pairs, they will have to get recoded as 3 dummy variables. One for the L2, the second leg pair, that will be 1 if it's a measurement on the second leg pair and 0 otherwise. Likewise for L3 and L4. So then from these 3 variables, you can tell which leg pair you're talking about. There will be, if they're all 0, then you know it's from the front legs. And if any one of them is 1, you know it's one of the other pairs of legs. And you wouldn't have any case where both L2 and L3 were 1. Only one of them will be 1. Thankfully, R does this for you automatically. In some other popular statistical software, it doesn't. You have to do this yourself. There are some advantages maybe to having to do it manually, and that there are some decisions to be made in this coding, and R just does it for you automatically. However, there are ways in R to be very precise about how you want them coded, which we'll cover a bit today. So I don't think there actually are any advantages to being forced to do it manually. Which brings us to model formula, which are these are the most straightforward way that you can define a linear model in R. There are lots of different functions that take model formula as their input. A few examples here: AOV, analysis of variance, linear model, generalized linear model, and Cox proportional hazards. And as you saw, box plot does, a lot of plotting functions do as well. So, so you need to know about model formula. The basic format of it is, on the left side, your response variable, and then this tilde, which I've found is very difficult to locate on Italian keyboards. You might have to copy and paste it from somewhere. And on the right-hand side are the explanatory variables. And you can read this as the response variable is modeled by the explanatory variables, or is modeled as a function of the explanatory variables. Here is an example for a linear regression with two variables, y the response variable and x the predictor. So this is just a simple linear regression. The model formula would be y is modeled as a function of x. That's all there is to it to create a simple linear regression. So let's go ahead and do it with the spider legs example. We're going to subset here just to look at the first set of legs. So just that first two, so we have those two boxes, and then I'm going to use this LM linear model function to model friction as a function, or as described by type, where type was push-pull, using this spider subset data set. And let's take a look at a summary of what we get. It's a very informative summary function that LM has. So it tells you exactly, so this is an object, we've stored it in memory now, and it keeps internally what the original call was. So if at some time later you just have this fit object, you can see how it was created. We have a 5-number summary of the residuals. So it's telling us the residuals vary from -0.33 to 0.76. We've got the first quartile, the median, and third quartile. I don't know why you necessarily would want that, but it's there. And then this next part is the most important part for your purposes, most likely. These are the coefficients of the model, along with some inference on those coefficients. So we've got two coefficients here. The first is an intercept. So you'll notice, even though we didn't specify anything about an intercept in here, it got added automatically. Most of the times you want an intercept, so the model formula interface assumes an intercept unless you actually remove it. So the model here includes an intercept, and it includes this variable type push. And we have coefficients or estimates for each of those. So can you tell me, if you were to write out this equation now, what would the equation look like? The equation for predicting friction coefficient from the type of leg in this first pair of legs, what would it look like? This is a simple linear regression.
So 0.92
Mm-hmm.
equals to minus 0.51 plus the error.
Not quite. So
0.9.
mm-hmm.
The B0. Like y.
0.92 is the beta 0. That's right.
And so it's y equal to 0.92
Mm-hmm.
minus 0.51 x.
Yeah, and what is x? What is x?
Is the type variable of the function.
Mm-hmm.
Binary variable.
Right, it's the dummy coding of that binary variable. So it has been coded so that if type is pull, it's a 0, and if type is push, then it's a 1. So our prediction for the friction coefficient will start with 0.92, and then if the type is push, we will subtract 0.51. So you could write the equation as y equals 0.92 minus 0.51 times x, where x is this recoded so-called dummy variable. One if push, and 0 if pull. Does that match the way it is here? Yes, that matches the way it is here. The coding is it's 1, type is 1 if it's pushing, and 0 if it's pulling. So if your dummy variable x is coded that way, then your regression equation, the systematic component of it, is y equals 0.92 minus 0.51 times x. So,
No, maybe it's later. So the type is significant.
yeah, so having the regression equation, that's nice, but what we really want to do probably is infer whether there is a relationship between leg type and friction coefficient. So the rest of this column helps us to do that. The second column provides a standard error on this estimate. So you've learned how to take a standard error and turn that into a margin of error and a confidence interval. The estimate is t-distributed, so you are able to use this estimate and standard error to calculate a t-value. If you just took this estimate divided by the standard error, it would give you this third column, the t-value. And from the t-distribution, you can get a p-value. So this first p-value is actually not terribly useful. This is telling us that the null hypothesis here would be that the intercept is 0, that the average friction coefficient overall is 0. So that would be if the spider were on, I don't know, an air hockey table or something, and it didn't move when it shuffled its legs. Not a very this is not a very useful p-value, but the second one is. So this second estimate we can interpret as the difference in friction coefficient for pushing relative to pulling. And it's saying that the friction coefficient is 0.51 less for pushing than it is for pulling. From the standard error, we could convert that into a 95% confidence interval just by multiplying it by 1.96. And from the t-value, we get this very small p-value. So that is telling us that the null hypothesis of no difference between pushing and pulling is not very likely, or it's not very likely that we would have observed so large a t-value if that were true, that there were no difference between pushing and pulling, and the difference we observed were just due to random sampling variation. So probably the most important parts of this table are going to be this row. This gives us our estimate of the magnitude, how much pushing versus pulling matters, the standard error that we can use to construct a confidence interval, and a p-value against the null hypothesis that this coefficient is 0. R gives these significance codes. Some people care about them, some people don't. I think that the historical reason behind them is that many people correctly say that p-values that are very small, like less than 0.001, are very sensitive to your assumptions. And if your p-value is less than 0.001, that means you have a 1 in 1,000 chance of having made a type 1 error. That should be good enough for you, rather than having to know the exact p-value. It is fairly customary now to report exact p-values, but I do think it's a good idea not to take these tiny values too literally, because most likely, if you're wrong, it'll be for some reason other than sampling variation anyways at this point, whether it's 10 to the minus 14 or 10 to the minus 4. It's probably not a type 1 error. A few other things I'll just comment in this output. There's a residual standard error. That's the standard deviation divided by the square root of n for the residuals. The numbers of degrees of freedom for this whole model, that has to do with the number of data points we have minus the number of coefficients that we've estimated. We have this R squared coefficient of determination, which you can think of as the proportion of variability in friction coefficients that was described by this model, by pushing and pulling. And you can even think of it as this being 57% of the variability in friction coefficient being described by the systematic part of this model. And finally, we have this F statistic that gives us, you'll see, basically the same p-value as we had here. And I'll talk a little bit about F statistic later. So this is based on a t-test, and this is based on an f-test, which happen to be comparable when there's only 2 levels for a binary variable. In general, though, this p-value you will be able to think of as a p-value for your entire model. Is your entire model, if you've included several variables or variables with several levels, has it provided a statistically significant reduction in the variance of your residuals compared to a model with intercept only. So here, because there's only 1 row added in addition to the intercept, these p-values are the same. But if there were more rows in this table, these p-values would be different. And this would be an overall p-value for your entire model. Degrees of freedom, there are different ways to think about them, but they are generally the number of data points that you have the number of independent observations minus the number of coefficients that you estimate.
So in this case, minus 0.
Let's just take a look at the we have 68 observations in spider.sub. Oops. And 66 degrees of freedom. And that's because we've estimated 2 coefficients here. It's not always that simple, but in a simple model like this, it is. Which is why it's useful having your software tell you what the degrees of freedom is, because sometimes it can be complicated just to say off of the top of your head. And in some types of models, it's even non-integer degrees of freedom, which is hard to think about and calculate. But in this case, it's just the number of observations minus the 2 estimates that we've made. I just wanted to show you, for the purpose of making reports, that there are some facilities in our Markdown that will help you to make nicely formatted regression tables and also analysis of variance tables, which I'll put one in later. Is formatted HTML, or if you're using LaTeX to produce PDF, can do PDF. And actually, this was why I ended up. You notice the look and feel of the presentation today is different than the previous ones. I was using IO slides before, and I'm using Slidey today because I found that this table looks terrible in IO slides. So I changed over to Slidey, and I actually realized that I like Slidey better. Like, I kind of like these different colors, and I can fit more text on the page, and the contents. I can go to any part of the presentation. It's kind of nice. So after having made 6 lectures for you in IO slides, now I'm saying Slidey is better. Anyways, so this is just those 2 key rows of all of that summary output put into a nice HTML table. Just to really drive in the interpretation of those 2 coefficients, here's a graphical representation of them next to all of the data points themselves. So we have a number of data points for pulling and a number of data points for pushing. The intercept is the mean for the reference category. So the reference category here, you can tell from looking at this coefficient. How can you tell what the reference category is? The reference, remember there is, when you code a binary or a categorical variable, you have one reference category and then comparison categories. The reference category with a binary variable is the one that's coded as 0, and the comparison category is coded as 1. So what's the reference category and the comparison group here? Pull. That's right, pull is the reference category. And we know pull is the reference category because it doesn't have a coefficient. It's the reference. The coefficient here for type push tells us how different the pushing friction is from the reference category. So in that equation where y equals 0.92 minus 0.51 times x, 0.92 is our prediction, our expected value for the reference category for pulling. So if for these front two legs, we want our expected value of the friction coefficient, if it is pulling, is 0.92, and if it's pushing, it's 0.92 minus 0.51. And so we can see these two coefficients nicely in this figure. The first line here, this green, is the intercept term, that 0.92. And you can see that is the mean of the reference category pull. So our coefficient is just the mean in the reference category. And then the type push coefficient tells you that you subtract, was it 0.51, if they are pushing type legs. And the intercept minus this coefficient gives us the mean friction coefficient for the comparison category, and this coefficient directly gives us the difference between the two categories.
And so you can understand from this that pull gets higher values than push.
Yeah,
without even plotting it, you can.
Yeah, you can understand that from this negative estimate, because it tells you that if it's a pushing type leg, you have to subtract 0.51 for the expected friction coefficient. What would happen here if we recoded the data so that the reference category was push and we got a coefficient instead for type pull? How would this table change? So we're just switching the reference category. So now suppose the reference category is pushing legs. What will be the difference in means, or the difference in expected values for pulling type legs? Maybe we'll look at it here. So instead of this being the reference category, pulling, we'll have pushing be the reference category.
Yes.
Right, so what will happen to the intercept term then? What would the intercept look like on here? What happens to this green line?
So it will be like going from above to.
No, the green line is still the mean of the reference category. So the intercept is the mean of the reference category. So what would be the intercept if we change pushing to the reference category?
It will be 0.41.
Yep, so 0.92 minus 0.51, that's 0.41. That would be the new intercept. And what would happen to this row, the second row?
It becomes plus instead of minus.
Exactly. So the intercept would be 0.42, and if we drew it on here, it would be from 0 up to 0.42 here. And then our coefficient, it would say type pull, and it would just be in the opposite direction. It would be positive. So this is an example of how your variables are coded has an effect on your regression output. And I'm going to give you some tools for controlling that coding so that your regression output can look the way you want it to. So you will have the coefficients that you want, and also so that you can be sure that you haven't made a mistake in the coding of your variables.
Because I remember, I don't know which formula I used, but in mentioned in general that the type is significant, but then you have to find out
Right.
in what way.
So I can tell you why that might happen.
I usually
One way that might happen is if type was not coded as a factor, but it was coded as an integer. In that case, there's no reference category anymore. So it would not tell you type push. You would just see type. So this is an example of how it's good to be familiar with looking at this table and noticing something like that the level of your factor is missing, and that is probably because it was not a factor. And you can get very different results by having a variable coded as numeric or integer instead of factor.
And if it's categorical, again, it's a
If it's categorical, it should be a factor. Yes.
not only if it's binary.
Not only if it's binary. So imagine in this case, we have the leg pairs L1, L2, L3, L4. If that was instead 1, 2, 3, 4 and numeric, your regression means something completely different. So speaking of a categorical variable as the predictor, let's do it. So now instead of friction described by type, do friction described by leg and using the full data set. And I'm using Xtable again just to produce the coefficients table. So we have an intercept now, and we have coefficients for leg L2, leg L3, and leg L4. So what is the reference category? L1, yep. What is the mean friction coefficient for leg L1? The front legs? Yep. What's the mean for the second pair? For leg L2, what is the mean friction coefficient? Yeah, 0.83. Yep. Yep. And for leg L3? Yep. Yep. So each of these is compared. These coefficients are differences from the reference. So it's telling you that L2, our estimate is that it had the increase in friction coefficient compared to the reference is 0.17. And for L3, it's about the same, 0.16, but for L4, it's much bigger, 0.28. We again have standard errors and p-values on each of these. We have kind of a marginal difference for leg L2, also kind of marginal, but under 0.05 for L3, and a very small p-value for leg L4. We are sort of missing something in there in that in this regression, we are mixing together pushing and pulling. So there's a very important source of variation that is missing from our model. So this leg L2 and leg L1, this includes all of the measurements for both pushing and pulling. So quite likely these p-values would be much smaller if we included pushing and pulling, because all of that difference between pushing and pulling has been treated as residuals, as random error here, as sampling error. And once you add to the model another term that will account for that pushing versus pulling error and remove it from your sampling error, you're going to find these p-values getting much smaller, most likely. We'll see what happens. So those were all just simple regressions of one variable. You can add more just as follows. So y described by, let's say, x plus z. Note that this does not mean that you're adding x and z. This is special model formula language. This just means that you're adding it to the model. If you actually had two variables that you wanted to add, you have to put this I around them. I stands for identity, and this would actually add your values of x plus the two variables in your model. Does this make sense? The important thing, you probably are not going to need to use I. You could always just create a new variable first in your data set that is the sum of them. What's important to know is that x plus z, that's not the usual meaning of plus there. It doesn't mean you're adding them. It means that you're putting them both in the model. So here is our spider friction model with both type and leg in the model, and our regression coefficients table. So this looks kind of like a combination of both of the tables that we had before. We have an intercept, we have a coefficient for type push, as well as the coefficients for legs L2, L3, and L4. What do you notice about, do these look familiar? This coefficient type push, these coefficients for L2, 3, 4, aren't they the same? Let's look back again. So minus 0.779 and then 0.171628. No, the intercept is different, but these coefficients are the same. Okay, this one is not the same, but what was that? Minus 0.51. These three are the same. But you'll notice that these p-values are now much smaller than they were. So that is because all of that variation that was due to pushing and pulling that we treated as random variation is now being assigned to push and pull. And the reason that the estimate for push is not the same is because we only looked at the first set of legs. We looked at a subset of the data when we did the type push model. If it was on the whole data set, this estimate would be the same. So when we add more variables to the model, these coefficients stay the same. That is that the difference between the average L2 second row legs and first row legs, that average difference is the same whether or not you're also accounting for pushing versus pulling. But what's different is the amount of residual variation, because we've taken, when we added another variable, we've taken some of the residual variation and explained it by that additional variable. So it has a huge impact on our p-values. So I think we're getting a better model here. It's definitely better than that one. The one that was just friction described by leg, that was a terrible model because all that big difference between pushing and pulling wasn't accounted for at all. So it's definitely better. It's still a little bit problematic because you remember we saw that the difference between pushing and pulling varied by leg. And that's not accounted for in this model. There's just one coefficient for type push. So regardless of what leg pair we're looking at, there's a difference in, if for pushing coefficient of friction, it's minus or 0.78 less than for pulling across all of the legs. And we know that that's not what the data looked like. Which brings us to interaction or effect modification. This is modeled fairly simply just by creating a product of the two variables and fitting another coefficient to it. This is an example I used for another course, but so it's a little bit out of context, but I like it. This is an example of interaction or effect modification of the effect of coffee on your time to complete a task as it's modified by time of day. So here is an example where, so we've got amount of coffee, either 1 cup or 3 cups, and this is what your data might look like if coffee were effective at reducing your time to complete the task, but that effect is not modified by time of day. So we have a main effect of amount of coffee. Coffee reduces the amount of time it takes you to complete a task. And we also have a main effect of time of day, in that in the evening we're faster to do the task than we are in the morning, regardless of how much coffee we've had. So this would be an example of there are two main effects, coffee, time of day, but there's no interaction between them. In this second one, this would be what we might see if there were an effect of time of day, but no effect of coffee. So we're faster at doing things in the evening, but coffee doesn't help. So, and here is an interaction where these lines are not parallel. So what we have here is in the morning, coffee seems to help. It reduces your time to complete the task, but in the evening, it actually hurts your ability to complete the task. In the evening, it makes you too jittery and makes you slower to do the task. So that is an interaction or an effect modification. So you could state that result as saying that the effect of coffee is modified by time of day. And here's another modification. So in both of these cases, you'll see that there is no overall effect of time of day, in that the average time to complete the task is the same whether it's morning or evening. There's also no main effect of coffee, in that the average time to complete the task is the same whether you've had 1 cup or 3 cups of coffee. So neither of the main effects here are significant, but the interaction seems to be important. Here is another example where there is no main effect of time of day. The average is the same. There is an effect of coffee, in that on average, if you've had 3 cups of coffee, your time to complete the task is less. But that effect is modified by time of day, and it's only observed in the morning. So maybe that's enough to, unless you want to have a hand at trying to interpret each of these two. I want to try, how would you interpret this? Is there an effect of time of day?
Time of the day?
Yeah.
Yes.
Yes, in that you're slower in the morning than in the evening. Yeah. Is there an overall effect of coffee? A main effect of coffee?
Yes.
Why do you say that?
Because in the evening, 3 cups.
Well, in the evening there's an increase. In the morning there's a decrease, but overall there's no effect. So here the main effect of coffee would be nothing.
There is nothing.
No main effect. But you'd be missing out on something if you didn't include the interaction, because you see that it actually depends on time of day. So you would need an interaction term here to know that there is some importance of coffee, even though the average effect is 0 over morning and evening. Right, the average time in the morning is 25 seconds, and the average in the evening is still 25 seconds. So there's no main effect of coffee, but there is an interaction with time of day. These, by the way, are called spaghetti plots. If you fit a term with an interaction in it, you can make spaghetti plots and see lines like this. All right. So this is a good time then to give you a little bit more of a systematic description of creating the model formulae. So you learned first this plus, which just means include a variable. You can use a minus to delete a variable from the model. A colon to add an interaction between two variables. So this is a useful thing to know, and we're going to use it in just a minute. You can also add interactions using the asterisk. So this is a shortcut to say include the main effects of each of these variables and their interactions. So this is actually the most common way that I would add interaction terms. But if you have many variables, there's a combinatorially increasing number of interactions. You end up with, if you have 2 binary variables, there's just 1 interaction term. If you have 3 binary variables, then there are 1, 2, 3 pairwise interactions and 1 3-way interaction. If you have 4, I don't know, I can't count anymore, but it gets very large. This is a way to control the number of interaction terms that you have. This would mean include all of the interaction terms only up to 3-way interactions. So, well, with U plus V plus W, there are only 3-way interaction is the most that you could have, but you could say to the power of 2 to only include interactions between pairs of variables, not interactions between 3 different variables. And use -1 to delete the intercept. There are lots more. If you look up model formulae in R, it's practically a programming language that describes design of experiments, but that's way more than we could get into in this course. But once you have things like nested designs where you have, you know, subgroups, and you can just describe all of this. The model formula makes it, and the way that dummy variables get coded automatically, like things getting turned into those 0s and 1s, makes it almost frighteningly easy to perform all kinds of different regressions. So in this example, y described by u plus v, if both u and v are factors, it'll be an ANOVA. If they're both numeric, a multiple regression. And if they're a mixture, that gets called an ANCOVA, analysis of covariance. I've also heard this listed as a criticism of R, that it makes it too easy to do fancy regressions, and that it's a bit like when you're starting to learn regression, it's like handing a chainsaw to a child or something, because you can do great damage with this very simple interface. But if you understand your variable types and you pay attention to reading your table of coefficients in the output, not just looking at the p-values, you benefit from this simple elegant interface. All right. So what is going on behind the scenes with this model formula? I didn't actually put in the I do it later, the looking for interactions between push pull and the leg pair. So I want to just introduce you to the concept of a design matrix. This is how R encodes your dummy variables. So recall this multiple linear regression model. We've got a slope and we've got a coefficient for each of these variables. This can be written out alternatively in a matrix notation, where each of our observations is one element of a vector. So our, what was it, 68 observations in that subset would be a vector of 68. Each of the predictors, in that case it was push-pull, would be an element in this, would be an element in one column of this X matrix. Should then be multiplied by your coefficients, and the residuals would be added. So this is the matrix representation of the linear model. And the book spends like pages and pages talking about matrix representations of regression. I'm going to spend basically only this page because I didn't want to get bogged down in matrix algebra. But in this representation, so that we've got a column of ones, I don't know if you remember how you multiply two matrices, but for the one on the left, you go across rows, and the one on the right, it's columns. So it would be 1 times beta 0 plus x1 times beta 1 equals y1. And then for your second row, 1 times beta 0 plus x2 times beta 1 plus your residual would give you y2. So if you had beta 0 and beta 1 and your residuals, this would let you calculate all of your y's from your x data. This x, it's just your data, but it's also your design matrix, because there can be various ways to represent your data once you have categorical variables. Remember how we defined x? There, it depends on your reference category. There are different ways to define those x's. However you define them, you would write out your data in this way, and this x would be your design matrix. So there's nothing mystical about the design matrix, even though when you just hear about it, a lot of the soft libraries that you might want to use for linear modeling, the most popular ones out there, Lemma, DESeq2, they use model formula interfaces, and they also use design matrix interfaces. And the reason they use both is to give you total control over the model that you fit. Here's a very simple example of a design matrix. So we just have we have a predictor that we're going to call group. It's 1, 1, 2, 2, and we turn that into a factor, and then just give the right-hand side, because this is just x, so tilde group, and turn that into a model matrix. And this is what it looks like. So for if we want to predict a y from this group, we would add the intercept to everyone. That was added by default. And then we would add this group 2 coefficient only when it's a 2. So this matrix makes explicit the coding of a dummy variable here such that 1 is the reference group. So there's no contribution to from this coefficient for the reference group, and it's 1 for the comparison group, which is 2, just to make things a little bit confusing. So you see intercept and you see group 2, which is your comparison category. What if we didn't put factor around that 1, 1, 2, 2, and this is going back to that comment that you had earlier. Look at this now, it says group, it doesn't say group 2 anymore. It's a small difference, but it's an important difference. And now instead of 0, 0, 1, 1, we have 1, 1, 2, 2. It hasn't been recoded as a dummy variable. These are just the actual numeric data points themselves. So this is a completely different design matrix than the one we saw on the previous page. So it's very important that you pay attention to what data classes your predictors are when you do regression. Let's add one more variable, keep it as a factor, and you see that it adds another column to the model matrix. And so these first 2 data points that are the reference category, they get values of 0 for both the group 2 and the group 3 dummy variables. Then for the ones where it's 2, you see they get a 1 under the group 2 variable. And where it's 3, they get a 1 under the group 3 variable. So here a k level, a 3 level factor has gotten recoded as 2 dummy variables. It chose 1 as the baseline group, but you know how R chooses a default baseline group when you have something like push and pull? How does it decide whether push is your baseline group or pull is your baseline group? It's alphabetical. Yeah, which one is the reference group? It's done alphabetically. Whichever one comes first in the alphabet will be your reference group. It has no way to know, so that's what it does. But you don't have to live with the default if you know this re-level function. So I created group as a categorical variable where 1 was the reference category, and then I re-leveled it with 3 as the reference category. And now you see I have dummy variables for group 1 and group 2 instead. Here's an example with 2 variables, diet 1 and 2, sex, female, male, and a 2 variable model. So each of these is just binary, so they get 1 dummy variable. So diet 1 is the reference, and diet 2 is the comparison group. So the second half of them are diet 2, so we get 1s for those four variables, or for those 4 observations. And sex female becomes the reference because F comes before in the alphabet. All of the males, numbers 3, 4, and 7, 8, get a value of 1 under that dummy variable. So this is, the model matrix is how you can know explicitly how your data was recoded by default. And you can check, you can put it in a spreadsheet even, you can put it in Excel, you can use View to look at it in the little spreadsheet viewer in RStudio and understand the model that you're fitting. And finally, let's add an interaction term. This is the same as the previous model, but we've added an interaction term for diet and sex, and you see that it is 0 except when diet is 2 and sex is male, then it's 1. So this is going to be the amount that is added to the expected value of the response variable for diet 2 for men compared to women. Well, it's an interaction between diet and sex, but the coefficient fitted will be the amount. You could think of it as the increase in the effect of diet for males. If you wanted it to be the increase in the effect of diet for females, then you would have to put these ones where these are females. They would have to go there. So for the increased effect of diet for females, it would be a 1 and a 1 here, and a 0 and a 0 there. The important point there, which is something that they emphasize in the book, is that your model matrix doesn't follow naturally from your experimental design. For one experimental design, there are various ways that you might model it in a linear model. And there are defaults that the model formula will create for you, but the defaults won't always have the coefficients with interpretation that you want. So here is the spider legs regression with an interaction term added. So all of these, we've still got our estimates of the main effects for type and for the legs, but we have these additional interaction terms which tell you how much the effective type changes for each of the legs. So, and these are significant for 2 of the legs, meaning that difference between pushing and pulling is bigger for legs L3 and L4 than it is for the reference. So this coefficient we could interpret as, so type push, this is the difference for the reference category, L1, difference between pushing and pulling. This tells you that difference, this interaction term tells you that difference is 0.1 greater or more negative for leg L2, 0.38 bigger for leg L3, and 0.39 bigger for legs L4. So we're able to directly, from these coefficients, say whether the push versus pull difference is different in any of these legs compared to the reference category. But what if we wanted to ask that same question for L3 versus L2? Is the push versus pull difference different for leg L3 versus L2? We can't do it directly from this table. We could subtract these 2 estimates, and that would give us an estimate, but we wouldn't have a p-value or a standard error on it. And that is where, so you could go and redo this fit with L2 as the reference category, or you could just define a model matrix that has exactly what comparisons you want in it. And then you will get estimates, standard errors, and p-values for each of those estimates. And so the desired contrast here would be that interaction term for L3 minus the interaction term for L2. And this is just an example of a shortcut for defining that particular contrast. And I don't want to get into it other than to show this particular interface. It just lets us say a -1 for tight push leg L2 and a 1 for tight push leg L3. So it's the difference between the interaction term between type and leg L3 and type and leg L2. So it's a coefficient that we didn't fit in our original model, but using this little convenience interface, we're able to get another estimate, standard error, and p-value for this new contrast that is what we want. And this can be very practical in your own experiments where you have hypotheses about differences between certain sets of groups. You can, rather than living with the default of everything against a reference, you can specify all of the contrasts that are of biological interest to you and get those coefficients and their p-values directly. So we are almost done. It's been a long lecture. Model matrices, you don't always have to use them, but if you want to customize the model that you're fitting, you may have to use them, or you may want to use them. All of the major differential expression packages will recognize them, or the model formula. And I think it's time to take a break. I have a little bit more to go over on analysis of variance and multiple testing. These are quick though, but we've been going for an hour and a half. So let's take a quick break, then I'll wrap those up. And then today's lab, I'm not assigning any new lab assignments. I saw that, I think, Serena, you're the only one who handed in a lab from last week. So we're yeah, so we'll just spend more time on that lab exercise today, as a way to get you further along on your projects as well. All right, and I am going to pause our hangout. Thanks everyone for tuning in. Hope you're having a Buona Pasqua. Okay.